This is Annette Kirkland, and welcome to Beyond the Gates. This season, we're going to be highlighting ERDIC's legacy of groundbreaking research and cutting-edge technologies. Join us as we explore how innovation continues to drive progress in military and civil works missions. I am delighted to have with me Dr. Emily Asenath-Smith. She's a research materials engineer with the Cold Regions Research and Engineering Laboratory, otherwise known as CRREL, and we're going to be talking about Icebreaker, solving the problem of ice adhesion. Good morning.
Good morning, Annette. It's great to be with you.
I am so glad that we can talk about this amazing subject this morning, but we're going to talk about something even more fun. Tell me about yourself and your background.
Yeah, I started out my scientific training in chemistry, and I was really passionate about high-temperature ceramics, which seems like a big contrast to the title that we have here today. So if you just bear with me, I'll make it make sense. I completed my bachelor's degree in chemistry at a small women's college called Mount Holyoke College in South Hadley, Massachusetts. And because of my passion in ceramics, I continued on to Alfred University and did a master's degree in ceramic engineering. And finally, I completed my PhD at Cornell University in material science and engineering. And what's really, I think, what characterizes my background is that I started formal research as an undergrad. And I really got trained in how that process works and really just how to address research, mentorship, and all these things. So in undergrad, I was focused on surface science and interface chemistry and hybrid materials. For my master's research, I looked at hybrid crystal lattices, which is kind of a different take on a similar idea. And we were trying to control thermal and electrical properties of technical ceramics. And finally, in my dissertation research, I pulled these two background areas together under bio-inspired crystallization, so trying to grow crystals the way biology does, like seashells or bone. And I learned a lot about water and how crystals grow from aqueous solution. And I think this is finally what's been super important for my research on ice. Mm-hmm. I definitely got a good understanding of water and how crystals grow from water. So it's, after graduation from Cornell, lots of my mentors and, grad student associates thought it was super strange that I accepted a position at an ice lab. But the funny part was I saw them to be totally related. I was like, ice is a crystal, it sticks to surfaces. We can maybe control that by using different approaches of chemistry. And all along the way, we're going to need to characterize the properties of materials. So to me, it's very connected. And now when I tell that story, people say, oh, I see what you're talking about. But initially, it seemed a little weird. This woman who loves high temperature ceramics takes a position leading research at an ice lab.
And this is going to sound crazy, I know, but I've never heard of ceramic engineering.
Oh, it is, at this point, it's kind of become a subset of material science and engineering, and then sometimes it was in mechanical engineering departments. But essentially, we're talking about technical ceramics. Like, for example, the silicon chip that's in your cell phone is considered a technical ceramic. Silicon wafers that it's built on are not, they're not metal alloys. It's a semiconductor, and that's that whole semiconductor industry. It can really be identified as ceramic engineering. So I want to point out one really interesting thing about ice that people don't really realize off the bat. So everyone thinks of ice as a cold material. And I think that's because in our ambient environment where humans live, ice needs to stay frozen to exist, right? And so, but I want to draw your attention to sort of the relative temperature scale that materials have. So imagine, I love high temperature ceramics, and glass and ceramics are related fields. I'm sure some folks have seen glass blowing on television or even in person. And you see that it's molten. It's kind of flowing, it's glowing, it's red, it might be orange or yellow. These are hot materials. And if you take and look at the full temperature scale, where the hottest temperature a material can have is its melting point. And then you think of what fraction, like what fractional value are you at of its melting point? So imagine, let's just say, for example, that we have a glass with a melting point of 1,500 degrees Celsius.
Mm-hmm.
And if we heat that glass up to 1,000 degrees, then we're at 2/3 of its melting point, right? And if we think about that do that same thought exercise for ice, that actually ice that's at -20 degrees Celsius is actually still at 90% of its melting point. So it's hotter than a molten glass when it's frozen. And so if you followed any of this, the summary of the matter is that ice is actually a hot material.
You're blowing my mind right now.
Ice is more like a high temperature ceramic than a lot of people realize.
Mm-hmm.
And so again, this whole concept of crystals and temperature has really, and aqueous chemistry really made it pretty seamless for me to transition from what appeared to be a disparate field into ice research.
Wow. Okay. I have a feeling I'm going to learn a lot today. So, so what is your role at ERDIC?
Yeah, it's I'm always busy. So I guess the first line of my position description should say that your role is to be really busy. Like you said, formally, I'm a research materials engineer. In that capacity, I founded and I'm the lead investigator for the Advanced Materials team at CRREL in Hanover. And essentially, this is, we function a lot like an academic research group. We have a highly interdisciplinary group of researchers, technicians, and students from a range of backgrounds and academic levels. And in total, there's about 10 of us. And we're doing research on a wide range of topics that involve ice and materials for cold regions operations. And so this is kind of the heart of what I do. I am very engaged with my team. We have weekly group meeting. We have weekly cleanup. I have individual meetings with folks. I mentor them. I've currently had a junior researcher just get promoted through the RGEG paneling process, and she's been leading some really great topic areas. So it's super exciting to see folks under me growing. And so, yeah, we have a lot going on. I try to pair people in sort of subgroups, for lack of a better word. We sort of address 3 topic areas related to mechanical engineering, materials science, and chemistry. And so we sort of have a structure around those 3 topic areas, which to me are really materials science and engineering. So in addition, I'm the lead investigator for the ice adhesion facility at CRREL. And in this capacity, I lead both research and development activities as well as testing and evaluation services. So essentially, ice adhesion is sort of, the field that refers to trying to mitigate ice. And so there's a lot to be done there, and I think we can talk more deeply about that as the conversation goes along.
Let's jump into the subject matter. As you say, your research involves ice adhesion. What exactly is that, and why is it important to study?
Yeah, so ice adhesion refers to the issue of ice sticking to surfaces and creating operational hazards. So, for example, think about ice sticking to airplane wings and how it negatively impacts drag and lift, so planes end up grounded or getting sprayed with de-icing fluids. Essentially, the field of ice adhesion is closely related to such things as ice mitigation technologies and how we stop ice sticking to surfaces, or how do we efficiently remove it once it's there. For the most part, the current technologies that exist to mitigate ice involve systems that weigh a lot, are energy intensive, or like the de-icing fluid, that are environmentally unfriendly. So to address these limitations, there's a whole lot of research and activities going into engineering the surfaces themselves, whether it's by chemical modification, mechanical modulation, or physical structuring, essentially to cause ice not to stick in the first place. And so this is called passive ice mitigation. So because you're not adding any energy input. And so the ability of a surface to passively resist ice adhesion totally depends on the chemistry, the physical structure, as well as the thermal, mechanical, and optical properties. So this is really the bread and butter of material science. It's really understanding thermal, mechanical, optical properties. And so to engineer a surface that will resist ice sticking in the first place or cause ice to shed under its own weight is what I like to call the holy grail of the field of ice adhesion. And there's a lot of activity going into engineering surfaces like that, essentially making really fancy paints, right? Some kind of coating that you can put on a steel or aluminum engineered material to change that material's interaction with its surroundings. And so there's a whole lot of advanced coating technologies in this field of passive ice mitigation, which is essentially ice adhesion.
Does
that make sense?
It does. I'm just sitting here so fascinated. I mean, it's just amazing that there could be something that ice would not adhere to. That just blows my mind. So,
well, that's why I called it the Holy Grail.
Absolutely. And you probably have a lot of people's attention right now. So how will this research help the military?
Oh, it's very broad reaching. So, the military has vehicles, sensors, equipment systems. I mean, even soldiers themselves and all of their components. And none of this stuff works well when it's covered in ice. And so, I mean, it's not hard to imagine that a ship encased in ice can lose its balance and capsize, which I think some of the listeners have probably heard in the crab ship shows that show some of that. But also, aircraft lose lift and drag, like we discussed. And then on smaller scales, you can have icing issues with goggles and face masks and some of these smaller component items that individual soldiers wear. So the military needs ice mitigation solutions for a whole wide range of applications and material types. I can just say that we are addressing ice adhesion research that relates to fabrics and plastics, and not just metals. So I like to say to people, ice adhesion is a hot topic because there is a lot going on and it's an extremely diverse research space.
And it's just so mind-blowing that, what important work you are doing and for people to understand what's going on in Hanover, New Hampshire.
Well, it's really neat. So CRREL, I was just telling someone this morning. So CRREL was founded in 1961, and the reason why it was put in Hanover, New Hampshire was because the Army Corps of Engineers kind of put out a request for bids to build this laboratory that would be CRREL, and Dartmouth submitted a bid for that because they have a rich history of polar science and engineering. And so the topic area aligned for them, and so that's how we ended up here. And they still have a nice research lab. And we collaborate with them as much as possible. It's a niche space, but there's quite a lot going on.
Absolutely. Doesn't sound like your job is very boring at all. So how did you become interested? Well, again, I know we talked about this a little bit earlier, but how did you become interested in ice adhesion? And what are some of the challenges you face in the field when I'm sure there's a lot of challenges?
Yeah, totally. So what I thought was really neat is that my research on ice adhesion directly leverages my background in surface chemistry and interface science and hybrid materials and crystallization, right? So if you want to engineer a surface to change how it interacts with its environment, that's a surface chemistry topic. That's something I started as an undergrad in chemistry. If you want to think about how, ice forms on something, ice has a crystal structure. It's a crystalline material. And so you probably need to understand quite a bit about how crystals form and nucleate and grow. And that directly leverages my master's and PhD work. And then just having this all be in water and really needing to understand the complexities of water and soluble additives versus insoluble additives and how that affects ice and how it forms on surfaces. And that's totally related to my PhD research. So what I really, love about this is that it leverages my background in new ways. And there is, like you said, there's always a new challenge, and I don't mind it. Some of the challenges that we face in this field, though, are related to the lack of standards. So if say you have a concrete specimen or a metal, and you want to know the tensile strength or, the compressive strength or how much load it can bear, there are these various organizations around the world who have put together some standard testing approaches. So, the American Society for Testing of Materials, or, ASTM standards, ISO standards, SAE has some, so Society of Automotive Engineers. And essentially, these standards will outline in very specific detail the geometry of the specimen, how, the parameters that you program into the instrument that you're going to load it with, and very specific details around testing materials. And this way, in the end, you'll get results that you can share with someone who tested a different or a same material in a different laboratory. And so it helps to sort of standardize testing approaches across, research field broadly. And what's really challenging about the field of ice adhesion and ice material science in general is there are no standards for this. If you go into those databases that I just rattled off, and you type in a search for ice, you will find one for aircraft, you will find one standard for controlling ice on aircraft, one standard for de-icing sidewalks, and then the rest of the standards are for ice cream machines and hockey rinks.
Okay. Different formulas for, I guess, the whole different subjects. Okay.
And it's really, none of this is, here's how strong an ice cover is that's floating on a lake, right? The military wants to cover wants to traverse frozen lakes. How do you know how strong it is? Well, the ASTM, ISO, SAE databases have no information on that. How do you measure the ice adhesion of some advanced coating system? There is nothing in that database at this time. So that's the biggest challenge, is figuring out ways. Essentially, there's almost as many ice adhesion tests out there as there are people developing these coating technologies. And so how do you compare numbers? You kind of can't. And if you can, it's qualitative, and it's only materials that were tested in an identically same geometry, conditions, et cetera.
Right.
So a lot of the research that my team is doing is actually focused on how do we test? How do we grow ice on a surface? How do we remove the ice from the surface? How do we analyze that data? What type of data should we have in the first place? And so we have this this ongoing research project that is focused on researching how we test and how we analyze data in ice adhesion tests.
Okay, so I understand there's a new facility that helps support this work, the Ice Adhesion Testing Facility at CRREL. Can you tell us more about it?
Sure. So I started at CRREL in 2015. And like I said earlier in the discussion, CRREL was founded in 1961. So they've been at this business of ice for a pretty long time. And like I just told you a minute ago, too, there are no standards for testing ice adhesion. And so along the way, researchers at CRREL in the 80s and 90s timeframe had developed a couple of index tests for assessing ice adhesion of various materials, and they would use the test in the exact same geometry in the exact same way. And one of them is called the 0-degree cone test, and another one is called the lap shear test. And our facility, our ice adhesion facility, does have a web page if folks want to read more about those. And those were sort of index tests. So if a customer or industry academic is developing some kind of coating technology and they really wanted to get some sort of independent third-party verification, they could contract the ice adhesion facility and send their samples, and we would, CRREL would test them and send the data back. And so when I started in 2015, the ice adhesion facility was primarily engaged in this independent third-party testing. There wasn't a lot of research happening. They had done some research to develop the 0-degree cone test, decades earlier, but it really was just sort of, a testing service that was being provided. And so I came and I said, well, I'm a materials engineer. We have this problem of ice adhesion. I've done a lot of surface chemistry. I should be able to, let's develop a material. And so I started looking into it, and I said, well, like we just talked about a minute ago, how do you test it? How do you analyze the data? Oh, there is no standard way of testing this or analyzing the data. And I was like, it became clear to me that the field does not need more coatings.
Mm-hmm.
The field needs more information on the coatings that have been developed, because there's plenty of coatings out there that look fantastic. We just can't transition them to real field applications unless there's numbers and data that's meaningful. Mm-hmm. And so that's, where I backed up and said, hey, I'm going to research how we test and how we analyze the data and develop a physics-based experimental and analysis approach for ice adhesion. And we, basically took it all the way back to the drawing board. And at the same time, we still do provide testing services, but how I describe it is we, have our research and development activities, and then we have our testing and evaluation activities. And that gives us a really broad gamut of experiences, interactions, opportunities, customers. And so, yeah, there's never a dull moment, for sure.
Well, the thing is, you literally are the subject matter icebreaker, because as far as, hey, let's do this. I mean, I love that. So you recently received a patent for your invention of a vertical draw system and method for surface adhesion of crystalline materials. Can you explain what this invention does and how it helps your ice adhesion research?
Sure. Yeah. So I was kind of alluding to that in my last response, that
right.
We really had to go back to the drawing board and build from the ground up how we were going to adhere ice to surfaces, what geometry we were going to use, how we were going to delaminate it from the surface, and really building out deliberately building an ice adhesion experimental approach that was designed not just to make a coating look good, but to actually assess a broad range of materials and provide quantitative information. And so one of the challenges that we had was needing to grow ice on a surface and control the microstructure at the same time, and not have all of the difficulties that arise when you use molds to encase water and then freeze it on a surface. Mm-hmm. Then you have to remove the mold, and very often you end up damaging or interfering with the ice material interface somehow. And so because of my background in crystallization, I looked at this and I said, well, if we're just taking water and we're freezing it on a surface, this is just, we're crystallizing something from a melt. And there are documented techniques for doing so. It's just normally people using those techniques, they want to grow a single crystal, and we wanted a polycrystal. And so we came up with ways to transition such a technique to growing ice on surfaces. And what's really cool about it is, one, it's automated. So the vertical draw system, we basically set our sample in there, and we use a computer to execute the program, and it drops the surface down to the water, or the substrate, I should say, to the water surface, and then slowly steps it away, growing ice and adhering an ice laminate to the surface, and giving us control over the microstructure. So that's one technique that's been really great. And the second patent that we recently received is for the actual test geometry. And so that test geometry, again, was designed, developed, engineered to be compatible with physics-based fracture mechanics approaches, so that we then would have a really scientifically defensible analysis approach. Mm-hmm. And so these two patents have been really important in just sort of demonstrating these incremental but very deliberate progression towards quantifying ice adhesion.
Wow. Well, this year we're celebrating how the labs came together 25 years ago to form one ERDIC, one organization of experts across multiple disciplines. How did you collaborate with other researchers or organizations in your ice adhesion research program?
Oh, great. That's a good question. So the multidisciplinary aspects of ERDIC are actually really special. And I tell people that very often, that we have these 7 laboratories and each one has a very specific mission space and expertise. And I feel passionately about mentoring my team, about collaborating. We have a huge number of collaborations, and foundationally, those collaborations are in ERDIC. And we've had productive collaborations that involve that broadly involve EL, GSL, ITL, and CRREL. Currently, in terms of ICE adhesion, we're collaborating with mechanical engineers at ITL to build a structural mechanical model. But I also want to stress that there are other ICE research topics that we're actively engaged in, and we have current collaborations with computational chemists at EL and also with civil engineers at CRREL to develop the technology to 3D print ice structures. So there's a little gem for you.
Wow. Well, so how many people are in your team?
We have about 10 right now. I guess if everyone was really standing in front of me, it might be 12. Mm-hmm. But four or so of those are intermittent students. So in terms of who's in the lab every day doing work, we're probably in the ballpark of 8 people.
Okay, great. So speaking of collaborating, CRREL teamed up with the USA Luge team to tackle a challenge related to ice. Can you tell us a little bit more about that?
Yeah, this is a super fun story that gets someone's attention right away. The USA Luge team reached out to me through the ice adhesion facility probably 6 years ago now. And the timing, so let me back up actually, because this is a kind of a really cool distinction around Olympic ice sports. So of the 3 sports that fly fast in sleds down ice tracks, there's bobsled, skeleton, and luge. And the bobsled sleds themselves are entirely manufactured actually by BMW. The runners, which are the metal actual parts that are in contact with the ice, everything is completely made by one manufacturer. Skeleton is the sport where a rider goes down head first, and they are in an individual sled that has where the sleds can be individually engineered, but the runners, that metal piece that contacts the ice, is provided by the Skeleton Association. On the other hand, or in contrast, so we're moving in a direction of more and more sort of engineering leeway, the luge sleds are engineered individually, and also the runners, the actual metal piece that's in contact with the ice, can be made by them. So what's really cool about luge is that these athletes are technically savvy to a certain extent, because they have so much engineering freedom around their sled. And so it makes them stand out in the field of sled sports. So that's the background on the luge team. So therefore, they're able to reach out and say, hey, we want to know how better to engineer our metal runners so that they go faster on ice. And that's basically what they reached out to me. And they said, well, if you know how to make things, if you know how ice sticks to things, then you must know how to make it not stick to things or materials to move quickly. Mm-hmm. And so at this time, 6 years ago, the timelines for them to make engineering modifications to their sleds and systems wasn't well lined up with the timelines that we had. So we didn't get our collaboration off the ground. But they, reached out again just last year and said, hey, we're ready and our timelines look great. And so we started to build this collaboration, at which point it became clear that some of the material development that they're working on is solidly within the scope of a collaboration that CRREL has with South Dakota School of Mines. And so basically, built that relationship there. And so it's really cool that we get to study these really new advanced alloys that are being engineered at at South Dakota and then test them out at a whole range of speeds, right? So the Army's not that concerned with moving 80 miles an hour on ice. But what we learn about really high speed friction scenarios is also very useful to the lower speed or looking for high friction. So we're studying the gamut and using sort of the U.S. luge application as an end member of that spectrum. So I should stress that these research activities that involve the luge team are pretty new and still developing. So we don't have results. We can't tell you that, hey, we solved the high friction problem or high speed friction problem. But I can say that we're working diligently and really collaboratively with a pretty diverse team on this high speed interactions between ice and metal alloys. So stay tuned, and we'll try to keep you informed when we do solve that problem.
That sounds great. I know everyone out there listening will be like, okay, now I'm going to pay attention to the luge program now. So with the Olympics,
yeah, exactly. Just look for gold medals.
Right.
The U.S. luge team.
Well, see, and the thing is, though, ice skaters, they don't need this, right? They don't need to go super fast. So,
yeah.
So what are some of the other current or future projects that you are working on related to ice adhesion?
Yeah, so we've been at this long enough that some aspects of our ice adhesion research have matured to the point that we're working on transitioning coating technologies to field applications. So like I said, I realized, hey, I don't need to develop a new coating. There's plenty out there. I just need to be able to get good numbers that mean something. So, technology managers can make decisions to deploy these cool materials. And so what we're doing is, we're essentially trying to develop the data set that will help the military make decisions about deploying passive ice mitigation technologies for various assets. So one example has brought us into a field scenario. So we put together a couple of field sites in northern latitudes to help us with this. So how does the coating itself hold up after dozens and dozens of freeze-thaw cycles throughout the winter and ice and de-icing cycles? And two, getting to larger length scale substrates. So in the laboratory, we're working on substrates that are, a couple centimeters big or up to maybe 6 or 8 centimeters big. And in the field, we can look at a panel that's 1 meter in diameter or something much larger, and understanding how length scale and performance scales across length scale is super important. So basically, we set up some field sites. There's one in the Bay of Fundy off the coast of Eastport, Maine. It's called Treat Island. And we've got we have some panels deployed out there and a weather station and some monitoring. We also have a field site set up in Alaska in Fairbanks. And then we have one here in the yard at CRREL. And so then basically after a couple of seasons of exposure, we reevaluate the coating integrity. We might retest ice adhesion in the laboratory to say, okay, is this still performing the same way or has performance degraded, and by how much? And this way we can actually provide an asset manager with some information that says, yeah, you know what, if you coat the hull of your ship with this advanced coating technology, it's actually going to reduce the energy required to remove ice from that ship by X% for X period of time, right? So it's exciting to be moving in that direction because, some of these lab scale experiments can get really tedious, and developing this analysis, it's a marathon. It's not a sprint. So, yeah.
But you learn something new every day, do you not?
Oh, we sure do. That is for sure.
So what would you like listeners to learn from this valuable conversation?
Yeah, I guess the thing I tell new folks on my team is that research is a long process. It's hard. If it wasn't hard, people would have already done it, right? And research rarely proceeds in a linear fashion as you initially conceived it. Whether or not the research is ultimately successful depends on thinking creatively, thinking outside the box, improvising, reprioritizing. It's a very dynamic process. It's challenging, it's ever changing, and for some people that's not a good fit. But for me, that's actually what I love about my job and where I work. We are provided the leeway to challenge ourselves and develop solutions to unusual problems in a really unique mission space of cold regions. Mm-hmm. And so, my work is never boring. And I encourage folks on my team to think this way about research, because if you really expect research to be some sort of predictable, linear process, you might find yourself discouraged and disappointed and not actually tap into the richness and excitement of research and discovery.
Well, and I just want to thank you and your team for making such a difference in the world, because you definitely do.
Thank you, Annette.
Thank you for listening to Beyond the Gates, Season 3, Episode 8. I've been speaking with Dr. Emily Asenath-Smith, and she's a research materials engineer with the Cold Regions Research and Engineering Laboratory. And we've been talking about Icebreaker, solving the problem of ice adhesion. Thank you again.